Did you ever notice that we only ever see one side of the moon? The moon's period of rotation equals its period of revolution around the Earth. That's a really interesting fact. The rotation of an object is something that spins about on an axis that points down through it. And the revolution is the orbiting of one object around another. Here, the moon around the Earth. It's really interesting that the moon rotates with the same speed at which it revolves. Funny enough, if it did not rotate, a feature on its surface, such as these craters you see in this image, would always point in the same direction in space. And then we would see it move into and out of view. That into and out of view would make it look like, from the ground, that it's rotating, when in fact it would not be. But because this is so weird, we look up at the moon in the sky and we think that it's not rotating. So let's actually go through and look at all the phases of the moon, the nature of the month, all these things, and show why it is rotating. Let's go through all the phases. First we start with waxing crescent, and then we get to approximately almost a week in, we get to the first quarter moon, which is half illuminated, and then we go to the waxing gibbous moons, which are not fully illuminated. Finally we get to full moon, and then it's waning gibbous, which is more than half illuminated. Then we finally get to third quarter, which is roughly half, and then less than half illuminated are the crescents, the waning crescents. And I leave the black spot portion open simply because that's called the new moon. New moon is when the moon is in the same direction in the sky as the sun. So let's see how we get those phases. But first, let's take that really quick trip into why the moon rotates at the same rate as it revolves. Okay. The moon shows its phases because sometimes it's on the sunward side of the Earth and sometimes it's not. So what we have here is a cartoon of the moon and the Earth, and I've put a red line through the moon just to demark the side that we see from Earth. Yeah, this is kind of a goofy thing because the North Pole is not through the center, through the equator. So I probably should have used a different little cartoon there for the Earth, and I guess I could. But the most important thing is we're pretending that we're looking straight down on the North Pole of the Earth or the North Pole of the Moon. We're also pretending that these axes of rotation and revolution are all the same, which is not true. But anyway, most important thing is that red line. So let's now see what happens when we let it go. As we see, the moon is going around the Earth, and that red line is staying fixed with respect to the moon. But yet, if you look closely at the red line, that would seem to indicate that it's rotating. Because if the red line weren't rotating, it wouldn't change orientation. In fact, it changed 360-degree rotation. You can do that for yourself by just kind of thinking about it, taking a pencil and put it in your hand, and then rotating it. The stick will rotate around. Now, if your hand is holding the stick, and it goes around, you can actually rotate the stick by moving your wrist around in a circle and keeping the pencil in orientation the same way as your hand. Another way to look at it is this. As the moon goes around the Earth, we can either have option A or option B. Option A is the moon is not rotating as it revolves. So if the moon did not rotate at all as it revolved, then that black spot, which is some feature like a crater, would always be pointed in the same direction. To us on Earth, it would look like the black spot is moving across the moon. But in reality, the moon is not rotating on its axis. It is certainly revolving around the Earth, but it certainly is not rotating on its axis. However, in B, to the right, we see that the orbit is still the same, where it's orbiting around Earth, but now we're allowing the moon to rotate on its axis at the exact same rate as which it revolves. That black spot is staying fixed with respect to the position, it's always facing the Earth. Now, that's interesting. This is a result of tidal locking for the Earth and Moon system. The Moon used to be, during its formation about 4 billion years ago, when it was formed, it was much, much, much closer to the Earth than it was today. It also was going around the Earth a lot faster, and it was spinning a lot faster. those two things decreased. First, the distance went out. First, the moon went to a greater distance over time, and the rotation slowed until it matched the month. That's called tidal locking. I talk about that in another video. So let's actually now look at what we mean by a month. First, we're going to review what we talked about last time, which was the sidereal versus the solar day. That's kind of helpful. The sidereal day is when the sun comes back to the same position in the sky with respect to the distant stars, but the solar day is when the sun comes back to, say, due south at noon. That's the difference between them. It's the same position in the sky with the same place with respect to the ground at the Earth, but the sun will change its position with respect to the distant stars. And that's because the Earth is going around the sun. Similarly, we can derive sidereal and synodic periods for the moon going around the Earth. The first one, which we'll call the sidereal month, which is approximately 27.317 days. The sidereal period is the time it takes for one revolution of the moon around the Earth with respect to the distant stars. So that's going from spot A below, and as the Earth goes around the sun, it gets to spot B. In that time frame, the moon has gone around the Earth and gotten back to that place. That, if you're looking down from above the solar system, the sidereal month is probably the most intuitive definition of what a lunar orbit would be. But we're based on the Earth. So we use the synodic month. That's 29.53 days. The synodic month is the time interval between successive similar alignments of the moon and sun. From the standpoint of an Earth observer, the synodic month is probably our most intuitive definition. When we look at the moon, the easiest thing is to recognize the phase rather than precisely where it is among the stars, its position. So that's how we do things. As such, the synodic month is the time between, say, full moons or between, say, new moons. Both of these are called syzygies, which are either conjunctions or oppositions, but it's when the sun, the Earth, and the moon are in a line. That's a syzygy. The difference from a sidereal month compared to a synodic month is because the Earth goes around the sun. So now we have these two different kinds of months. The synodic month, which we call phase to phase, or full moon to full moon, or new moon to new moon, or even crescent to crescent, a specific first quarter to first quarter, whatever you like to call it. That is 29.5 days. That is the synodic month. The sidereal month is much shorter, by 2.2 days, which means there's approximately an additional sidereal month per year compared to the synodic month. All right, let's see how that plays out together. And let's look at the moon's phases, and we're going to look at the synodic month phases at this point. So let's start here. On the left-hand side, we see the rays of the light from the sun. On the right-hand side, I'm going to show the various phases of the moon and their names. This is named a waxing crescent moon. I still use that funny little graphic, which, we're not really looking straight down on the Earth for this one, but hey, we're, what's a diagram among friends? It's the Earth. So the orbit is represented there, and now we have two different dashed lines. I've replaced the red dashed line previously and made it blue to indicate the far side of the moon and the near side. The far side we'll never see. It never is up in the sky for us to see from Earth. The near side is. But we now need a new demarcation, the side that's illuminated by the sun and the side that's not illuminated by the sun. As we can see, I've shaded out the side on the right-hand side because that's the side that's not illuminated by the sun. But there's part of it that we can see, and part of it, well, all of the side that we can see, more than half of it is not illuminated. As you can see, the grayish spot is a big chunk of it that is taken out, that is on our side, on the Earth side of the blue line, is more than half of it is grayed out. And a very small wedge is not. That corresponds to a waxing crescent. So that little disk on the lower left is represented on the right by a spherical distribution. The moon is a sphere, not a disk. So a little pizza pie wedge, like we see in the lower left, becomes that crescent wedge. So if you were to take the crescent wedge of the moon and look at it from above, it would look like that pizza slice. Well, it would be projected down. But we look at it from the surface of the Earth and we see the poles at either end. So the tips of the crescent, the horns of the crescent, are at the poles, the north and south pole of the moon. So now let's go forward. First, though, we call this a waxing crescent moon. Waxing crescent moons are somewhere between 90 degrees and 0 degrees elongation east of the sun. They set just after the sun sets. So if you see a waxing crescent moon, the sun will set and then the moon will set. Roughly speaking, this image of the waxing crescent moon is a 4-day-old moon, and the moon is in the sky, in the daytime sky, mostly during the day. Daytime sky, of course it's daytime sky during the day, but the moon is, of course, when it's in this phase, mostly up during the day. Now we move along to the first quarter moon. The first quarter moon, this is about 7 days since new moon, and it is 90 degrees elongation east from the sun. It is half illuminated. And why is it called first quarter? Well, it's 1/4 the way around, and 1/4 of the moon is what we can see to be illuminated. That's why we would call it first quarter. There's multiple reasons, but 1/4 the way around from new. So this moon then will set at approximately midnight, and it will rise at approximately noon. So let's see what we have next. And the moon goes around the Earth, and now we get to these waxing gibbous moons. The waxing gibbous moon will rise sometime in the late afternoon, and will be up most of the night, and then will set sometime a little bit after midnight. This is roughly a 10-day-old moon, and it has an elongation angle from the sun between 90 and 180 degrees. Next, we have the full moon. Full moon is 180 degrees away from the sun in the sky. It's about 14 days in, and yes, it's directly opposite the moon, the sun from in the sky, so it rises at sunset and sets at sunrise. Next, we go to the waning gibbous moon, and this is roughly 18-day-old moon. It's at 90 and 180 degrees west of the sun. This will rise sometime after sunset. It will be up most of the night and set after sunrise. Then we go to third quarter moon, which rises at midnight, and it's about a 22-day-old moon. It's 90 degrees west of the sun in the sky. It rises at midnight and sets at noon. Next, we go to the waning crescent moons, which rise just before sunrise. This is a 26-day-old moon, and the elongation angle between it and the sun is somewhere between 0 and 90 degrees west of the sun. So it rises just before sunrise and then stays up most of the day. Finally, we have new moon. New moon means we don't see it in the sky because it's in the same direction as the sun in the sky, and it's up all day. It rises at sunrise and sets at sunset. New moons are important because that's when solar eclipses happen. If it's new moon, then they can have a solar eclipse. That's what we call a 0-day-old moon or new moon. All right, so we're back to waxing crescent again, and the cycle repeats and repeats and repeats over time, and we've seen these happen throughout most of our lives. But now, sometimes there are people that say, well, hey, I see all this, but the moon's pretty big, and the Earth is really big. So a lot of people have this mistaken idea that the dark part of the moon that we see is due to the Earth's shadow. It is most certainly not due to the Earth's shadow. So let's see really why not. Well, first let's start off with the idea that the Earth is about 8,000 miles wide. That's about 12,730 kilometers or so. And now we're going to zoom out, and we're going to show how far away the moon is from the Earth. The moon is almost 240,000 miles away, which is 385,000 kilometers. The moon itself is only 2,100 or 2,150 miles across, or about 3,500 kilometers across. And there's only one time that the moon will be in the shadow of the Earth. And let's say if the sun is off to the left in this diagram, and then the moon would have to be off to the right, because look at that. That's a very tiny target. So now we're going to add the orbital path, and after we add the orbital path of the moon around the Earth, now we're going to zoom out and take a look. Look at that. Look at how many places that it's not in the shadow. The sunlight's coming from the left, and the Earth is a very, very, very tiny target. And I've tried to make these things as exact as I could in terms of their proportionate sizes. This is pretty close to it. So therefore, the moon is only going to be in Earth's shadow for a very small period of time, but it's not necessarily going to always be in the Earth's shadow when it gets on the far side of the Earth compared to the sun. This is a really important point, and this is why. It is completely why that the phases are not due to the shadow of the Earth on the moon. They are due to the positioning, the relative position of the Earth, moon, and sun in the sky. Okay, when you hear about stuff, occasionally you hear about in the news this thing called like a supermoon. What the heck is a supermoon? Well, the moon travels around around the Earth in an elliptical orbit, or it's not actually a circle. I was kind of deceptive in my previous stuff. It's not a circle. It travels in an ellipse. The moon therefore passes through a point closest to the Earth called the perigee, and a point farthest from the Earth, the apogee. And when the moon is at or near its closest point to the Earth at the same time as it's full, we call it a supermoon. Why? Because that's a great way to get people to come outside and go look at the moon and have a good time. It's also great for stuff, to relate to the news people. And you'll see stuff about the news. Oh, go outside and see today's supermoon. You won't miss it tomorrow. And people go, I missed the supermoon. It doesn't have a cape on it, not flying around. It's not 60 times the size. No, it's just a little bit closer than it normally is. And what's the difference between them? See, it's kind of a funny thing. But it will appear larger in the sky. But how much larger? Well, noticeably, but not necessarily to most people's eyes, but you could notice it if you know what to look for. So it can actually be up to 14% bigger because the moon's orbit wobbles and it differs depending on where the sun and Earth are in their orbits, and the exact distance on these closest and furthest points do vary. Here are the various sizes differences that we can have between a supermoon on the left and a micromoon on the right. A micromoon is usually nothing that makes news. A micromoon is when it's full and it's at apogee, when it's at its farthest point to the sky. So that's, the only difference between the micromoon and the supermoon is about 14%. And each of these is between, say, 34 arc minutes on the left and 30 arc minutes on the right. And 30 arc minutes is half a degree. 34 arc minutes is a little bit more than half a degree. So it's a little tricky to actually see these in the sky, but your eye can actually make the sound go, wow, it does look bigger. And it's not just because it's low to the horizon either. Having the moon low to the horizon is a psychological trick, not necessarily a reality trick. That's kind of fun. But supermoon, micromoon, what other some moon names? Well, there's blue moon, wolf moon, snow moon, worm moon, pink moon, flower moon, strawberry moon, buck moon, sturgeon moon, harvest moon, full corn moon, hunter's moon, beaver moon, and cold moon. All of these things are very traditional. They come from the Farmer's Almanac. The blue moon is just simply 2 full moons in one calendar month. And it's not that rare. It happens at least once a year. Blue moon, once in a blue moon. Okay, once a year is basically what that means. So if somebody says, oh, it only happens once in a blue moon, that's once a year. Good for them. Okay, but there are other kinds of moons as well. Months as well. But we're going to talk about the 3 other kinds now. There's the tropical month, the anomalistic month, and the draconic month. The tropical month is equinox to equinox, and the anomalistic month is perigee to perigee. And draconic month is node to node. Wow, what do those things mean? Okay, they are not described in this image, so I'm going to describe them to you briefly, then I'm going to show you a video. But first, the tropical month is a minor variation of the sidereal month, so it's like the one that goes from A to B. But instead of using the fixed stars, it uses the March equinox. The March equinox is the defining celestial longitude of right ascension in the equatorial coordinate system. It is where the ecliptic and the celestial equator meet on the ascending node. That is the definition of the March equinox. Because the Earth precesses on its axis, The equinoxes also slowly precess retrograde. This means that the moon arrives at this reference frame slightly faster than the truly inertial sidereal frame, and therefore the tropical month is slightly shorter than the sidereal month. By how slight? The period of precession of the equinoxes is about 26,000 years, so it's a very, very, very tiny change from the sidereal month. Next, the anomalistic month, which is an important one as well. The anomalistic month is also a variation of the sidereal month. It's a slightly different flavor, and it's about 27.55 days. Now, what is this then? Is the reference line is instead the line of apsides, meaning the line on the or between the 2 points on the moon's orbit between apogee and perigee, between the highest point in an orbit from the Earth and the lowest point, apogee and perigee. The line of apsides in the moon's orbit precesses about just under 9 years, and so it takes for the moon a little bit longer to reach the same point in the apsidal frame, say apogee to apogee, and it's a little bit longer than the sidereal month. Finally, of these 3 different months is the draconitic month or draconic month. That's 27.2 days. The draconic month is similar to the anomalistic month, except that instead of using the line of apsides, it is using the line of nodes. The line of nodes is the intersection of the plane of the moon's orbit around the Earth and the plane of the Earth's orbit around the sun. Let's get that again. The Earth's orbit around, so the moon has an orbital plane, and it's tilted with respect to the Earth's orbital plane around the sun, which is called the ecliptic. On one end of the line of nodes is an ascending node, and the other end is a descending node, meaning where the moon passes upward through the ecliptic going upward, and the other one where it's passing through the ecliptic going downward. The line of nodes precesses with a period of about just under 18.5 years in the opposite direction of the moon's orbit. Therefore, the draconitic month or draconic month is faster than a sidereal month. Once again, we have the tropical month, which is equinox to equinox. Anomalistic month is perigee to perigee. Draconic month or draconitic month is node to node. And now I got a little video that's going to show that, and we're going to see how these things differ in their appearance. We see first that it's passing by the equinox. That's the March equinox. And now it goes on its merry way, and there's the red line. The red line is the moon. Oh, wait a second. There's a total solar eclipse coming up on April 8th, 2024, when the node matches the full moon and the sun is right next to that location. That's how you get that. And that happens only very infrequently. So if we look really closely, let's just look at this again. And I've slowed it down a lot so we can actually watch it. The ascending node of the red line matches that of the ecliptic. And if they just line up perfectly and the distance from the sun is at, say, perigee, not apogee, then the moon will be the same size as the sun or a little bit bigger and totally covered for a total solar eclipse. Now this has been set up to be at New York City, so it doesn't quite cover it. You have to be in exactly the right place in order for the moon to totally cover the sun. And it's called the draconitic month. You can see the node of the intersection right there off to the right. It's called the draconitic month because Draco the dragon is said to live at the nodes, a historical dragon, and it eats the moon. That doesn't eat the moon, it eats the sun during eclipses. And that's pretty cool. Anyway, so that is the ascending node. It's the beginning of the draconitic month. Anyway, so the moon is traveling on its red line, which is the path that the moon takes around the Earth. That is the orbital path around the Earth. And the ecliptic is the orange line, which is the path that the sun takes, which is actually the Earth's path around the sun. So as the moon goes around, we see the phases. We also see a funny thing, because stellarium, which I'm using here to do this simulation, is making it look like that orbit is wobbling. But really what I'm doing, because stellarium is actually measuring the position in the sky of the moon from the Earth's surface, not from not from some location that is representative of, say, the center of the Earth. Oh, and what we just saw there was the descending node, where the moon's orbit goes through the ecliptic. So that's one, though we've just seen both nodes where the moon's orbit crosses the ecliptic, going down, and initially we saw it going up. There's also an orbital period with respect to the celestial sphere, which is the March equinox, which is where the ecliptic meets the celestial equator. So we're getting closer and closer to that, but we see it's kind of a bother to see the thing moving like that. If we really wanted to see it differently from the moon, we would pretend that the Earth is a dot in space and move from there. And now we're back to the point of Aries, or the equinox, and that's one of the months. And then we go back over here. Now notice we get to this ending point here, and the sun is no longer at the node that's on the lower right. So we have the ascending node of the moon's orbit, and we have the yellow line, which is the ecliptic. Once again, the tropical month is when we got back to that little point that had the Aries thing on it. That was the equinox to equinox. And that's just a point in the sky with respect to the celestial sphere. And that changes because of precession of the Earth's axis. I did not do the anomalistic month of perigee to perigee on this thing because that'd be just harder to see, and we'd have to look at a whole bunch of numbers in the upper left. But anyway, that's a little bit about months and lunar phases and all sorts of wonderful names and things. See you soon.